Hi, welcome to 1.4 Skills for Working with Radicals. Our success criteria. I can verify through investigation that the square root of A times the square root of B is just the square root of A times B. Okay, we will also learn how to simplify radicals. This is an example of a radical. And then we're going to learn how to add, subtract, and multiply radicals together. So first we want to look at the following table. And I'm going to get it started. I'm going to put in the first entry in column A and column B for the first row. And then you guys afterwards will go through and complete the rest on your own. And then I would like you to answer these three questions. Okay. First, I'm going to get this started though. The square root of 4 times the square root of 4. I plugged it into Desmos right over here, and I just got 4. Then in the next column, the square root of 4 times 4. Did that right over here, and I also got 4. So we could see those are actually the same thing. Okay, so what I'd like you to do now is just pause the video, complete the rest of these, and then answer these three questions. And I'll see you in a few moments. Okay, welcome back. Let's check our answers. So I've already done these ahead of time. And you probably would have noticed the last two. The answers are non-terminating decimals, so I've just kind of rounded them to just 2 decimals. Okay, however, we can clearly see, looking at this column, we notice that the results in each row are the same, right? 4 and 4, 5, 5, 31, 31. Okay, they're all the same. So we can just say they're equivalent. Okay, having said that, can we make a general conclusion about an equivalent expression for root A times root B? Okay, so notice here we've done a square root of something times the square root of something else. What is that equivalent to? Well, we can see it's equivalent to the square root of those numbers placed underneath the root. So we could say the square root of A times B. Okay, they're actually the same thing. You also might have noticed that whenever we multiply like radicals, like root 81 times root 81, we just get 81. It's like we drop the root. Okay. So another way to think about this is root 81 times root 81 is actually just root 81 squared. And when you square a root, that's actually undoing the process, and we're left with just 81. Okay, so we can make a conclusion about this. Root A times root A, well, we're just going to drop the root, and we're going to be left with A. Okay, now let's look at some vocabulary for radicals. So the radicand, when we say radicand, we're just talking about the number or expression under the radical, under a radical sign. The entire radical. Okay, this is a radical in the form root n. Okay, root n, we call this an entire radical. And there's just some rules for n. N needs to be greater than 0. So an example of this would be like the square root of 33. Okay, so this is considered a radical or an entire radical. And notice in our previous definition, the radicand, it's always the number or expression under a radical sign. This would be the radicand. This is the entire radical. So I'll just write that down real quickly for us. That's called the radicand. Okay, and the whole thing, we call that an entire radical. Okay, mixed radicals. So this is basically a radical where we have a number in front. So it's a radical in the form a square root b. Okay, and there's a couple rules to this. A can't be equal to plus or minus 1. And the other rule is that b is greater than 0. Okay, here's an example. We can have 2 times the square root of 3. So this is considered a mixed radical because we have a coefficient in front or a number in front. Okay, let's talk a little bit more about radicals. Okay, so some numbers cannot be expressed as fractions. These are called irrational numbers. Okay, some examples of irrational numbers. So pi is an irrational number because the digits keep going forever and there's no pattern. So it's non-terminating and no pattern. So uh, sometimes radicals fall into that same category, like the square root of 2. So Pythagoras came across this radical a long time ago when he was trying to come up with Pythagorean's theorem. And he was basically looking at this basic triangle, the 1, 1 square root 2 triangle. So this is a right angle triangle, and he was calculating the hypotenuse. And he had to calculate the square root of 2, and he got stumped. Okay, that's not an easy calculation to do, especially if you don't have a calculator. So this number, the square root of 2, if you try to calculate it, it never ends. The digits keep going and going forever, and there's no pattern. So sometimes radicals are in that form. So one type of irrational number is of the form the square root of n, where n is not a perfect square. Okay, if it was a perfect square, it would look like this, square root of 9. And well, that's easy. That's just 3. So this radical is just a rational number because you can evaluate it because it's a perfect square. But if you don't have a perfect square underneath, like 2, well, then we get something irrational. Okay, so when we're in this form and we don't have a perfect square number, we just call these radicals. An approximate value can be found for these irrational numbers using a calculator. So I can use my calculator to evaluate this, but it's not going to give me an exact value, okay? It's better to work with an exact value. So answers should be left in radical form when an exact value is needed. So if you need an exact answer, don't use your calculator to evaluate this. Just leave it the way how it is. Okay? Now, sometimes entire radicals can be simplified by removing perfect square factors. So we'll see pretty soon that sometimes these radicals are going to get bigger. They're not just going to be 2, but we're going to look at like square root of 50 and other numbers like that. We can actually simplify them a little bit further. And when we simplify them, we get a new expression, which we call a mixed radical. Okay, to do that, we're going to be referencing this nice perfect square table. Okay, here's a list of all these perfect square numbers. Okay, they're called perfect squares because you can square root them, right? The square root of 100 is 10. Okay, all of these are perfect squares. So when we simplify radicals, what we want to do is we want to rewrite this in terms of its factors, but we want one of the factors to be a perfect square. And we actually want it to be the biggest perfect square that fits in here. So this is what I am talking about. So the root 50, I would like to replace the 50 with 2 factors, and I want one to be a perfect square. So I could factor out 1, that wouldn't help. I could factor out, I can't do 4, can't do 9, can't do 16. I could do 25. Okay, 25 is in fact the biggest perfect square factor of 50. So I'm going to rewrite 50 as 25 times 2. Okay, and the nice thing is that if you remember just above in that investigation, we looked at the square root of a times the square root of b, and we determined that that is just equal to root a times root b. Okay, that means we can split this up into 2. So that means I can split this one up into 2. This is like my a, and this is like the b. So we would have root 25 times root 2. And now you can see why we picked a perfect square factor, because we can actually take the square root of that. And we would get 5 root 2. Okay, so that one is complete. Let's do a quick check. The square root of 50. The square root of 50, try it again. Okay, 7.07, and let's check 5 root 2. Do we get the same value? Yeah, we can see they are identical. Okay, so using those rules, we just simplified this to this. So this would be called the mixed radical form. All right, now this next one looks like the same one, so we're going to fix that. We are just going to change it real quickly. I'm going to erase what's in here, and it should have read the next one too, actually. Let's fix that while we're here. Okay, and it should have read 27, and the next one should have read 180. Okay, so root 27, what's the largest perfect square? So looking here, what's the largest one of these that fits into 27 evenly? Okay, it's 9. So we write this as the square root of 9 times 3. And I can split this into 2, root 9 times root 3. Square root of 9 is just 3, so we have 3 root 3. All right, so that is that one. Why don't you guys pause the video and try this one? Okay, so split this up into 2 factors, make one of them the largest perfect square possible. Okay, go ahead and hit pause. Okay, welcome back. Let's finish this one. So you might have found out this one took a little bit of playing around with. The biggest perfect square for 180 works out to 36. Okay, 36 is the largest perfect square that goes in. And we have 36 times 5. Okay, 36 times 5 is just 180, right? So now we're going to split up the roots. We have root 36 times root 5. And root 36 is a perfect square, so we just get 6 root 5. And that one is completed as well. Now we're going to look at adding and subtracting radicals. Okay, let's get started. Adding or subtracting radicals. So adding and subtracting radicals works in the same way as adding and subtracting polynomials. So when we add and subtract polynomials, we can only add like terms, okay? I wouldn't be able to add a 4y to this. It's not the same kind of term as the other. So this would give me 4y plus 5x, because these are like terms. So with polynomials, you can only add like terms. Or in this case, if we want to add and subtract radicals, we can only add or subtract like radicals. Okay, to add or subtract them, it says add or subtract the coefficients and then simplify. Okay, so here's an example. 2 root 3 plus 5 root 7. If I try to add those together, I can't. I can't because I don't have like radicals. To have a like radical means you have to have the same radicand. Okay, you need the same radicand. Okay, that's what we mean. That's what we mean by like radicals. Okay, the number under the root needs to be the same. Here we have that. So we can add those two because we have a root 3 here and a root 3 there. So it says to add or subtract them, just add or subtract the coefficients. So I'm going to add or subtract these. So since we're adding, I can do 2 plus 5 to get 7. So it'll be 7 root 3. Okay, let's do one quick check just to make sure this works. Okay, so is 2 root 3 plus 5, whoops, got to get out of that root. Make sure you do that on your calculators too. Plus 5 root 3. Okay, is that the same thing as 7 root 3? Yes, we can see it's exactly the same. So that's how we add or subtract radicals. Let's try one more. 9 root 7 minus 3 root 7. Okay, they're like radicals, so we'll write root 7 down, and now we'll just do 9 minus 3, 6. Okay, that's done. Do the next one. 4 root 3 minus 2 root 27. Okay, you might be tempted to say, Mr. A, well, those aren't like radicals, like you had said, so we can't do nothing. This one's done. Well, we can't do nothing yet. So if you remember root 27, this was one that we were actually able to simplify. Okay, so sometimes you might need to simplify first. Okay, so 4 root 3 minus 2. Root 27, we're going to pick 9 and 3, right? 9 was the biggest perfect square. So 4 root 3 minus 2. Now, the square root of 9, it's going to become 3. So I'm going to have a 3 there, then my root 3. Okay. So this, it's actually going to be negative 2 times the square root of 9 times the square root of 3. So that's how we get 2 times 3 times root 3. Okay, this 3 just comes from square rooting the 9. Draw a little arrow there. Okay, 2 times 3 is going to work out to 6. So we're going to have 4 root 3 minus 6 root 3. Right? 2 times 3 is 6. Okay, now we got our like radicals. Okay, they both have root 3, so we can just subtract the coefficients. 4 minus 6, negative 2. So we got negative 2 root 3, and that one is done. Okay. All right, part C. Why don't you guys try this one? I'm going to give you a hint first. Simplify the root 18 and simplify the root 8, and then try to add them. Okay, go ahead and hit pause. Okay, welcome back. Let's check our answer. 5 root 8. So root 8, we would like to write that as root 4 times 2. And then the 3, we would write as root 9 times 2. Okay, this is going to be 5 times the square root of 4. The square root of 4 is 2. And then we still have our root 2 at the end. Okay, this 2 just comes from square rooting 4. Our next term, we have 3 times the square root of 9. The square root of 9 is 3. And then we have our root 2 at the end. 5 times 2 is 10. 3 times 3 is 9. So we have 10 root 2 plus 9 root 2. Let's add those coefficients. We get 19 root 2. And that is our fully simplified answer. Okay, let's try this next one. Okay, this next one needs a little bit of fixing too here. This 3 shouldn't be 3. It should actually be 28. 28. Okay, let me clean it up again. Okay, that looks a little bit better. So just to read this out, make sure we have it. We have a quarter times the square root of 28. Then we have minus 3/4 root 63 plus 2/3 root 50. Okay, let's begin. So I'm going to write down the quarter. I can't do anything with that. Square root of 28, we're going to break that up into 2. We can do 7 and 4, right? 7. I'm going to write the 4 first. 4 times 7. Okay, now let's break up the next one. 3 over 4. And the square root of 63. Square root of 63, we're going to have to do 9 times 7. Okay, that's the biggest one that'll fit in. Sometimes it's going to take a little bit of time to do this. When you have a number like 63, you're going to have to work through all the perfect squares to find the largest one. And then sometimes you're just going to remember some of them because they're going to keep coming up. Like the square root of 50, well, that one's easy. 25 times 2. We've done that one already. Okay, my next line, I'm just going to evaluate these roots to clean it up. So we're going to have a quarter. The square root of 4 is 2. And then we have our root 7. Then we have minus 3 quarters. Square root of 9 is 3. Okay, the square root of 9 is 3. Oh, can't forget our root 7 at the end. Root 7. And then we have plus 2/3. Square root of 25 is 5. And then we have times the root 2 at the end. Okay, we're only rooting the number in front right here. That's it. Okay, a quarter times 2. That's going to give me a half. So we're going to have a half of root 7. Okay, then we're going to have minus 3 times 3 is 9. So we have minus 9 over 4 root 7. And then we have plus 10 over 3 root 2. Okay, and we can still simplify more. I see like radicals here. This one we can't do anything with, root 2. It's not like the others. These are like radicals, so we're going to subtract the coefficients. We're going to have a half minus 9 over 4 times root 7 plus 10 over 3 root 2. Okay, I just took these coefficients and I just put them in a bracket. And that way we can work with the fraction in the next line. So a half minus 9 over 4. We got to get a common denominator of 4, so we're going to multiply top and bottom by 2. So in the next line, we will have 2 over 4 minus 9 over 4 times root 7 plus 10 over 3 root 2. Okay, and I think we can squeeze this in on the last line here. 2 over 4 minus 9 over 4 is going to give me minus 7 over 4. Right? This is a common denominator, so we just subtract the numerator, 2 minus 9, to get negative 7. And then we have times root 7, and that is it. That one is done. Okay, there you have it. That is adding and subtracting radicals. Let's move on to multiplying radicals. To multiply radicals, we just need to multiply the coefficients together and then multiply the radicands together. That's it. And then simplify at the end if we need to. So let's do our first example. We got 2 root 3 times 3 root 6. All we have to do is multiply the coefficients together. 2 times 3 is 6. Okay, that's from the 2 times the 3. And then our next part, we're going to have the radicands together, the 3 and the 6. That's going to give us root 18. Okay, so we multiply the coefficients together. 2 times 3 gives us 6. Then we multiply the radicand together, the number underneath the root. 3 times 6 is 18. And then we simplify. Okay, my final line, I will have 6 times the square root of 9 times 2, which is going to be 6 times 3 times root 2, which will be 18 root 2. Okay, when you start practicing these radicals and working with them, you're going to get pretty good at them. And you're going to probably start shortcutting, and you're going to go from here to here. And that's totally fine. But make sure you're comfortable before you start doing that, because we don't want to be making mistakes. Okay, now this next one, we got some brackets. When we see brackets, we must always use distributive property. Okay. All right, so we're just going to expand that in or distribute in. So let's do this one first. So I'll erase that one. Let's just work on that one first. 2 root 3 times 4. Well, I know the 4 doesn't have a root with it. That's okay. If it did have a root, we would just do the 2 times the 4, right? And that's really what we're going to do right now, even though there's no root. We'll just do 2 times 4. We're going to get 8, and then we'll copy down the root 3. Okay, it's kind of like saying I have 2 root 3. Well, if you multiply that by 4, well, then you're going to have 8 root 3. Okay, that's how that works. Let's expand into the second term. 2 root 3 times 5 root 3. We're going to have to do the 2 times the 5. That's going to give us 10. And then the 3 times the 3. That's going to give us root 9. And root 9 is just 3. So we're going to have 8 root 3 plus 10 times 3. So it'll be 8 root 3 plus 30. Now, I also want to point out, when we're multiplying radicals together, root 3 times root 3 is always going to work out to 3. Okay? If you remember that rule, when we had like root 5 times root 5, well, that's just going to be the square root of 25, which is 5. Okay, our answer when you're multiplying like radicals is you're just going to get the radicand, the number underneath. So if you want to shortcut that in the future, when you're doing root 3 times root 3, we know it's just going to be 3. You can go ahead and do so. Looks like we'll have a chance in this one here. So we have two brackets being multiplied by each other. Okay, we have to take all the terms from this bracket and multiply it by all the terms in this bracket. There's a word for that, and it's called FOIL, right? That's what we do. So let's start. Root 3 times 2. That's just going to be 2 root 3. Now we're going to do the two outside terms. Root 3 times root 3. So if you remember, that's just going to be 3. Okay, we have to include the negative sign too, though. So I'm still going to write this out the long way. I'm going to do negative root 9. So I'm going to do this in black. Minus root 9. Okay, that's from root 3 times root 3. And I know that's just going to end up being 3 when I work at that later. Okay, and now the inside terms. 5 times 2. And then we'll do 5 times negative root 3. So 5 times 2 is just 10. And then 5 times negative root 3 will be minus 5 root 3. Okay, we never multiply these in. Like the 5 times the root 3, we don't ever multiply the 5 in, right? Root 15. That would be wrong, okay? If you have root 3 and then you multiply it by 5, then you're going to have 5 root 3. That's how the multiplication works. All right, we got like radicals here. So we can do 2 root 3 minus 5 root 3. So we're just going to subtract the coefficients. 2 minus 5 gives me negative 3. Minus 3 root 3. Okay, we still have our negative 3 here, and then we got plus 10. That works out to 7. Okay, and that one is done. This is our last example in this lesson, and we have another, looks like another FOIL situation, right? Okay, so let's go ahead and start that off. So we're going to do our two first terms together. 2 root 2 times 2 root 2. We're going to first do 2 times 2 to get 4. Root 2 times root 2 is going to be root 4, which is just 2, right? I'll actually leave that there for now. Let's leave it. Okay, let's do our next term. Two outside ones. 2 root 2 times negative root 3. Well, we're going to do our 2 times the negative 3 first. We'll get minus 6. Minus 6. And then we got root 2 times root 3. Well, that's going to be 2 times 3. So that'll be root 6. Now let's do our insides. We're going to have to do the 3 times the 2 to get 6. Sorry, I want to switch that to black. So we're going to get 6, positive 6, right? Because positive 3 times positive 2, positive 6. And then root 3 times root 2, root 6. Okay, and you probably noticed what happened here, right? Negative 6 root 6 plus 6 root 6. These are like radicals, so just subtract or add the coefficients. So negative 6 plus 6, that's going to all go to 0. That's kind of nice. And lastly, our last terms. 3 root 3 times negative 3 root 3. We're going to multiply the 3 times the negative 3 to get negative 9. And then we're going to multiply the root 3 times root 3 to get root 9. which is just going to be 3. Okay. All right, so we can see here that these guys cancel out in the middle. And then these also work out pretty nice too. Root 4 is just 2, and root 9 is just 3. So we end up with just 8 minus 27, which is going to be negative 19. Okay. Now, there is a shortcut for these. That's why I kind of had this written in here. So there's a shortcut for these because the middle term canceled out. Middle terms only cancel out when you have this scenario, okay? And when I say scenario, I mean you have the same thing in both brackets. You just have opposite signs in the middle. But the same first two terms, the same first terms and the same last terms. Just the sign in the middle is opposite. This is exactly like my a plus b times a minus b form, okay? Where like the 2 root 2 is a and the 3 root 3 is b. So we have a plus b, and over here we have a minus b. If you remember, this is a difference of squares factoring, and we factor this. Sorry, when we expand this, we end up just getting a squared minus b squared. Okay, the middle terms cancel out. So when we're factoring difference of squares, we usually go from this term to this term, but now we're kind of going the other way. We have this part where we know when we expand, we're just going to get there. So what this tells me is that instead of doing FOIL, I can just take a and square it. And a is going to be my first term here, which would be this. So if I square this, it's like doing 2 root 2 times 2 root 2. And it's going to work out to this, which eventually works out to 8. And then I can just square the last term, 3 root 3. It's going to be like multiplying by the other 3 root 3, giving me this here, which works out to negative 27. So I guess I'll just show you quickly what this would be. So this would be the shortcut method. This recognizing that this is a difference of squares. Sometimes I write this as DOS, difference of squares. So this is the shortcut. Okay, we're just going to grab the first term and then square it. So I would have 2 root 2 times another 2 root 2. And then I take my last term plus root 3. Okay, and I'm going to have to square that one. So 3 root 3 times another 3 root 3. Okay, and I know the sign in the middle of this needs to be negative. Okay, and working this out, 2 times 2 is 4. Root 2 times root 2 is just 2. Then we got minus. 3 times 3 is 9. Root 3 times root 3, also just 3. That gives me 8 minus 27, which is negative 19. So it acts as a little bit of a shortcut if you can recognize the difference of squares. Okay, guys, that's it for this lesson. And I hope this was helpful.